you, Olga. So I told you yesterday that what I wanted to do today is to prove the optimality of compressive sensing results. So what do I mean by that? So far we've obtained that if A is a matrix, let's take it with real entries of size m times n, let's say random. If it is random, it satisfies with high probabilities a restricted isometry property. So in particular, there is one matrix that satisfies this restricted isometry property. And so if we take delta to be a reconstruction map, so that will go from Rm to Rn. And so let's specify it to be the L1 minimization. So what was established is that if the number of measurements is of the order of s times a log factor, n over s, with the number e in front, that is sure to make this logarithm larger than 1. So if m is of this order, then we have a reconstruction property that will be valid for all x in Rn. So if I add s sparse x, I have exact recovery, so x will be equal to delta of ax. Now I want to also include stability with respect to sparsity defect. So if I apply my reconstruction on ax, and let me add maybe some noise, e here, this one is a vector, this one is a number, exponential 1. Okay, so if I measure that in LP norm, say for p between 1 and 2, okay, so I wrote that a little too close to the end. We have this reconstruction that will involve so a first term which is stability, so it will involve the how close x is to sparse vector in L1 norm. So this is sigma s means the best S term approximation, or the error of best S terms approximation of x in L1 norm. Right? And there will be also a term that contains okay, so I think I need to comment on that as well. The L2 norm of the error. And there are some s to certain powers everywhere. Okay. So here that will be divided by s to the power 1 minus 1 over p, so that when p is 1, that does not appear, and when p is 2 is square root of s. And here we have s to the power 1 over p minus 1 half. For, let's see, if p is 2, that does not appear. If p is 1, this is square root of s. And this estimate is valid for all x in Rn and for all, measurement error vector E in Rm. In fact, I haven't quite proved that. I have only looked at the case of exact sparse vector with no measurement error. This appears somewhere on a slide in lecture 2, if you want to go back to that. I did not include the proof. And on top of that, do you see something else that, in fact, is not exactly what I stated? So when you do the L1 minimization with measurement error, the constraint is y minus az in L2 norm less than some threshold eta, and eta was a bound for this, and in fact the estimates that I've shown included eta here. However, if you take now a Gaussian random matrix, and if you pretend you don't have measurement error, so you solve the problem with exact equality constraint, even though you know it's not true, this term will appear and not abound on it. So that is true. Also, it's valid for Gaussian random matrices, in fact, not for other random matrices, but it's a particularity of Gaussian that we can do that. For other, we can use other recovery method, iterative thresholding, where we would get this estimate directly with Gaussian and sub-Gaussian, with the disadvantage that to run those algorithms, we need some estimate on this S. But in any case, so this is what we have. So what I want to do is to say that if I want such a result, I won't be able to reduce the number of measurements any further. I won't be able to get something that is just proportional to S without a log factor. This log factor has to be there. Okay, so that's the plan for today. And in fact, this will be valid if we just look at stability. Stability for me means with respect to sparsity defect, and robustness means to measurement error. So we're not going to look at this part here. We're just going to assume that this is valid, that there is a measurement matrix, that there is a reconstruction map. So I don't specify anything. If there is a couple of those A and delta satisfying this reconstruction estimate, then M has to be larger than S times a log factor with a constant. Okay, so that's the plan for today. And I can turn on the projector now. So is it really clear what I'm trying to do? All right. So the title of the lecture is Optimality or Uniform Guarantees. I will explain this word uniform at the end. Remind me if I forget, please. So this can be seen with relating the problem with a concept in Banach space geometry. And in particular, this Gelfand width will play an important role. So before defining the Gelfand width, I'm going to look at, in a way, a compressive sensing width. So what we're trying to do here, right? So we don't impose anything on the measurement and reconstruction maps, but we say what is the best we can, or the worst we can do over class K for the reconstruction error, right? If I measure X, and then I applied a reconstruction map, how is this reconstruction error behave? So in the worst case, when I take the sup over K, right? And in fact, I want to choose the best possible A and delta, just with the assumption that A is linear. So if I take X to be Rn, this is just a matrix, and so no condition on delta. In particular, it doesn't need to be an algorithm. It doesn't need to be practical. All right, and so the infimum is taken over this A and delta. So that is a quantity that depends on this K and depend on X. In fact, the norm that is on the space X. So X typically is Rn, and the norm could be LP with P 1, 2, 1/2. I won't say much about the case of P larger than 2. So now what is the Gelfand width? So with parameter M, there's also a parameter M here. So suppose you take the same subset K, and you're going to slice it with subspaces of X that have codimension less than M or equal to M. Okay, so you take your subset K, you slice it with Lm, and then you look at the diameter in a sense. In fact, probably half the diameter. So you look at the diameter there, and then you try to minimize over the choice of Lm. Okay, so that's your Gelfand width. So maybe an illustration of what it looks like. If I take I'm in dimension 2 to be able to draw some nice picture. Maybe dimension 3 would work as well, but I would take the L1 ball. Right, so what is the L1 ball in dimension 2 is this. What is the Gelfand width? Can you see what it will be? Numerical value? So what you do, if you look at this definition, so you will slice this. So in fact, I will take m equal 1. I should also say that, but the other case are don't have interest. M equal 1, so my codimension 1 in the plane is just a line. So I'm going to cut that with a line, and I'm going to look at the, not really the diameter, the half diameter, that distance here, and I want to minimize that distance over the choice of the line. So where will the minimum occur? It will occur here. Okay, and what's the value here? It's 1 over square root of 2. Okay, so it shows you a little bit what this is on a small example. Now, why do I mention Gelfand width? Well, it is clear that the first compressive sensing width is relevant for measuring the how well we can do in compressive sensing. The second quantity is not clear exactly what it does, but we have this relation. If K is a subset that is symmetric, in other words, the opposite of anything that is in K is in K, then the Gelfand width is dominated by the compressive sensing width. That's one thing. So if you want to estimate the Gelfand width, you can estimate this. All right. In addition to this hypothesis, if you also suppose that the sum of two elements of K is A times an element in K, where A is some number larger than 1, then we have an opposite inequality that you can estimate the compressive sensing width by the Gelfand width with a factor A. In most cases, if we take K to be the unit ball with respect to some norm, this A is 2, because it says that the norm of the sum of two things that have norm 1 has norm at most 2. Okay, so K will in fact always be for us the unit ball of some norm space, and in fact always the unit ball of L1. So those two properties are satisfied. Therefore, Gelfand width and compressive sensing width up to constant are the same thing. Right. I am not going to do that proof, except maybe at the very end if you ask me, but I don't think I will have time. All right, so if we want to understand the compressive sensing width, we just have to understand the Gelfand width and vice versa. Okay, so the first thing we can do is to find an upper bound for the Gelfand width of L1 balls, right? So from now on, it's going to be K is the L1 ball. Yeah. In fact, this is on Tuesday. So Steve Wright showed you a proof of the success of sparse recovery by L1 minimization based on some result of Gardner F and Gluskin, I think he mentioned. Well, it's basically this upper bound. So what he was referring to. And we're going to simply prove that with everything that we've done this week. All right, so let's take a matrix A, which is a good matrix. So it satisfies the restricted isometric constant with delta S less than, okay, 1/2. Probably I should have put 1/3 in view of the slides from the second day, but M is the order of S times log En over. All right, so now you might say, well, didn't you write M of the order of log S times log En over S and not M? Yes, I did write that. It will come later on why, in fact, we can make assume one or the other. It's basically equivalent. Okay, and so this follows from the lecture from yesterday where I showed you the restricted isometry property for random matrices. We take delta to be, let's say, the L1 minimization map. So what we know is that x minus delta 1 of x, in fact, I've already written that here, is smaller than, so the distance to S sparse vector, from x to S sparse vector and L1 norm, and then there is this factor of S. Right? Now, I started with saying that x is in K, which is the L1 ball. So this distance here is certainly less than the norm of x, because if I approximate with 0, which is S sparse, I have that this is less than the norm of x, which is less than 1. Okay, so C over S to that power, if you look at what S is, roughly is m over log En over m to the power 1 minus 1 over p. Okay, so that gives an upper bound for Em because Em was the infimum we could. So if you take the sup over x, this is still valid, and then you take the infimum over A and delta, it's certainly smaller than for this choice of A and delta. So we have an upper bound for Em, and K in our case is the L1 ball, so we can use the fact that the Gelfand width is smaller than the compressive sensing width. In fact, it's smaller than that. It's also smaller than 1. If you look at what we're doing, the L1 ball, if you cut it, this diameter will always be less than 1. So there is a minimum of 1 and this log over m, and we have to put minimum of 1 and that, otherwise it's not correct. All right, so we do have an estimate, an upper estimate, okay, for the Gelfand width. Now I want to spend my time, some of my time, talking about the lower estimate for the Gelfand width. Again, this was obtained at the end of the 70s, beginning of the 80s, by Garnaev and Gluskin. The proof is, I think, 3-4 pages. Not too complicated to follow, but it would be an example of what I would call a unnatural proof, because you look at the proof, you understand all the steps, and if you want to do it again, you have no idea how they came to this. So not intuitive at all. I'm going to still rely on this result for now to give the optimality of the number of measurements, but later on I'm going to use method from compressive sensing to in fact rederive this lower estimate. Okay, so let's assume that what we've obtained as an upper estimate is also a lower estimate up to the constant in front that are different. Right, here everywhere I have p between 1 and 2. All right, so let's assume that, and if we accept it, we can show in this slide the optimality of compressive sensing results in the following way. Suppose that there is an A and delta achieving our targeted estimates for all x. So again, same trick as before. This is smaller than the L1 norm of x. And then if I'm looking at Em, in this case, is, for the same reason as before, smaller than C over this power of S. But Em is larger than the Gelfand width, which we've said, let's assume that we know that it is larger than that. So what happens is that this minimum is smaller than some constant here over 1 over S when we get rid of the powers. So two cases, either the minimum is 1, and so that tells us that S is small, or the minimum is indeed this log over m, and that tells us that m has to be larger than constant times S times the log factor. Okay, so now here's the explanation why I can remove this m and replace it by some S. Log of En over m is log of En over S times S over m. And then I separate the logs in 2. Okay? Now, this step here, I'm going to write S over m multiplied by m. Okay? S is smaller than m, so that if you look at the graph of x log x, it looks like that. it's bounded from below by -1 over e. All right, so m is larger than this term times a constant times m. Pass that on the other side, manipulate the expression a little bit, and then you get that m is larger than some other constant here times s times log en over s. Okay, so whenever you have to manipulate the log where you have log of n over m or en over m or en over s or a constant in there, you do the same trick, it will work. Okay, so that's why putting the e or not putting the e doesn't make a difference. Okay, so now I'm not happy with just accepting the lower bound for the Gelfand width. I want to know why this is true. And so that will be the next part of the slides. And there are basically two key insights. The rest afterwards, I'm going to still show you how it goes. But once you have those two key insights, the rest is just technical. The first one is that if you have a small width, it implies recovery by L1 minimization for large sparsity. Small width implies recovery of a large sparsity, vectors of large sparsity. So that's the first insight. The second insight is that L1 recovery of S sparse vector is only possible for moderate S. So the width cannot be too large, otherwise S would be large here, but that would contradict the second insight. Okay, so those are the two insights. If I make them precise, those are the statements I'm going to show you. For the first insight, that there is a matrix A such that every S sparse vector is a minimizer of the L1 norm subject to the constraint for S of the order of this quantity, 1 over the width to a proper power. Right, and if this width is small, S becomes large. The second insight, to formalize it a little bit, I have to assume that S is not equal to 1. So if A is a matrix such that every S sparse vector is recovered by L1 minimization, then M has to be already larger than some constant times S and then times another log factor, where the constant can be made explicit. So here you might say, well, isn't it what we're already trying to do? No. What we're trying to do is to prove that stable recovery for any pair of A and delta implies M larger than such a quantity. What we're stating here is that, in fact, if you look at L1 minimization and forget about stability, that already in itself imposes a number of measurements to be larger than S times a log factor. Right. So that fact about L1 minimization will be used to prove results about the stability of any reconstruction map. Okay. So I'm going to do the from those two insights. Again, right now I'm going to accept those two insights. I'm going to prove them. The slide after this one. But now, accepting those, here is how you derive the lower estimate. So suppose that, by contradiction, the width is smaller than a constant times this minimum mu to the power 1 minus 1 over p over 2. Right? So we want to prove, in fact, that this cannot happen, that, in fact, it has to be larger than that. All right, so if we set S to be of the order of, again, you would have to put floor and ceilings wherever it is necessary. But if you take S to be of the order of 1 over C mu, you can find a matrix A. So this is the first insight that allows you recovery of all S sparse vector for S to the order of that. Okay, this is what was on the other slides that we don't see anymore. Second insight, in that case, M has to be larger than S times log n over C2S. So S is, in fact, smaller than M smaller than m over 2 if we assume a sparse recovery. And we always said that m at least has to be larger than 2s. So I change the constant, although I don't need to do that. And then what I'm doing here, same trick as before, I can introduce en over m instead of n over c2m by changing the constant in front. And the minimum here is smaller than 1. So is this what I'm doing? No. What I'm doing is replacing s by its value, roughly its value, right? So it's 1 over c, and then this is mu. Now the minimum is smaller than the log, so when we take the reciprocal, the log, 2 log factors goes away. There is this 1 over m that goes on top. And if we chose c large enough at the beginning, the constant c1 prime is something fixed that I can exactly say what it is. So if I choose c large enough at the beginning, I obtain that m will be larger than m, which of course is a contradiction. Okay, so now those two insights. So the first one, why does small width implies recovery by L1 minimization for large S? All right, recall the null space property. If every sparse vector is a minimizer of the L1 norm subject to the constraint AZ exact AX, this happens if and only if the null space property of order S is true. That we've written in that way before, that I used in another way when I proved the success of L1 reconstruction. So the other way was by adding Vs to both sides. Now if you add V, well, that's exactly the same way. Right? So that's exactly the same thing as I used last time. So you add Vs to both sides and you simplify to get that. All right, so now let's write D for this width, shorthand notation. So because this width is the minimum of A, it is really the infimum, but in fact it's a minimum. We can take a matrix such that I identified basically this minimum space of codimension n with a null space of A. There's no real problem in doing that. So what we were saying is that if you normalize this to have LP norm 1, so no, K is the L1 norm. If you normalize it to have L1 norm 1, then the VP norm is less than the supremum that you can get, which is the what will appear in the Gelfand width, and then by homogeneity, you would add that V, the norm of VP, the piece norm, is less than this D times the L1 norm of V for all vector V in the null space. Okay, so now I take V in the null space, I take S of size S. What I can say, I can compare the L1 norm to the LP norm of VS. VS has only S non-zero entries, so there is this factor coming out in front. Now, the norm, LP norm of VS is certainly smaller than the LP norm of V as a whole. And now I'm using this property here. I'm introducing this D. And you see that if I choose S well enough, compared to D, in other words, 1 over 2D to the proper power, this here will be less than 1/2, and I will have the null space property. In particular, S sparse recovery with S of this order by L1 minimization. So that was first insight. If the Gelfand width is small, then you've got sparse recovery for S large. All right, so for the second insight, we will use this very important combinatorial lemma. So we relied on this lemma Holger and I and Alain Pajor and Tino Ulrich wrote a paper on Gelfand widths for LP balls with P less than 1. And the referee said, well, it's a nice paper, this lemma is interesting. In fact, it appears in, I know it appears in at least 2 other places. Then I've been to a workshop maybe a year ago where somebody else was talking, and we were talking at different times, but then he mentioned in his talk that what I showed, this combinatorial lemma, also appear in their field in discrepancy theory under another name. So, I mean, really it appears in several fields quite independently, so that probably shows you that's an important lemma. Right? So what does it say? It says, so consider all the subset of 1, 2, up to n of size S. How many of those do we have? En over S. Now let's consider those collection of subset of size S that do not intersect too much. Meaning that whenever you take a pair of 2 of those subsets, the size of the intersection is at most half the size of each of them. Can we get many of those subsets? Well, yes is the answer. We can get a number of those subsets n, which will be larger than n over 4s to the power s over 2. Now, that's of course not all subsets, but when we will take the log, it's about as much as we can do, because n choose s. We said that this is between En over S to the power S and N over S to the power S. And here, what is the number we get? We get N over 4S to the power S over 2. So compare the log of those two numbers. So you would have S and S over 2 in front, and then log of En over S or N over 4S. Again, not that different. Okay, so there is a large family of subset of size S that intersect pairwise, not too much. And that will be good for us. So what we're going to define for each subset Sj, we're going to define an S sparse vector, which is basically constant on Sj, 0 elsewhere. We take the constant to be 1 over S, so that Xj has L1 norm 1. What about the L1 norm of Xi minus Xj when I and j are different? So basically, you have the support that intersect not too much, of size less than over 2. So what's left out of the support is larger than S, because that part is larger than S over 2, that part is larger than S over 2. And then the entries are equal to 1 over S. On the support of Xi minus Xj. So this norm is strictly larger than 1 because of a strict inequality here. Okay? So now, here is the explanation of the second insight. What we want to prove is that if we have an A which allows recovery of S sparse vector for S larger than 2, or in fact every 2S sparse vector, so allows those reconstruction by L1 minimization of every 2S sparse vector, then we should get that M is large. Now, we will look at the quotient space L1, so quotiented by the null space of A. So what you have to just accept is that it's a vector space, and that the norm on that is the infimum of a V in null space of A of X minus V. Right, so what is this minimum? If X is 2S sparse, it's simply the L1 norm of X. Because this is a vector, if you apply A, you have the same measurement. It's AX minus A of V, which is 0. So it has the same measurement as X, but X is a minimizer of the whole vector with this measurement. So this infimum is in fact the norm of X. Right? So that's true for all 2S sparse vector. In particular, xj was S sparse and 2S sparse. So in this, the norm on the quotient space, it has norm 1. And the norm of the difference of 2xi minus xj, or their class, is larger than 1 because the L1 norm of the difference here was larger than 1. Okay. Now, it means that we have on the sphere of this vector space, we have points that are separated by a distance 1, and points that are separated by a distance 1. There cannot be too many of them. In fact, what I told you, the bound I told you yesterday about covering number is the same thing. The covering number is smaller than the number of points that are separated by a given distance, and that was 1 over plus 2 over that distance to the power the dimension of the space, which in this case is m, or at most m. Okay, so again, the size of a separating set cannot be too large, and precisely we have this bound. Now, when we take the logarithm, or in fact, recall that n is larger than that quantity, and take the logarithm, that gives you that m will be larger than, so there will be the constant coming from here, there will be s coming from there, and log n over 4s. And so you will rework that a little bit to transform the log as log of en over s. But that's basically the idea, and that will come, I guess, after the break. We take a little break, and then I have a little more information to give you. Right, I'm ready. But close the window because I'm cold. Okay, so there's something else I want to tell you apart from the optimality of the number of measurements. But before that, I want to also show you. So I've shown you the how we get the optimality by passing through Gelfand widths, and that is, has been the way to do it, the way people understood it. But we can look back at just what we've done, reflect a little bit, and say, well, we have some ingredients in the proof. And we don't need to go through the whole concept of Gelfand width. So there's a shorter argument to do that, which so you may take note because I don't think this has appeared before. So we'll do the following. We'll still use those subsets that intersect not too much. So I'm still assuming that I have A and delta for which there's no restriction on them except that they provide the stability estimate that we are after. Okay, so now still take S1 up to Sn of size S such that the intersection of Si with Sj is larger than S over 2. And so we know that we can find such a family of subset when n is larger than, so it was n over 4s to the s over 2, I believe. In any case, it's a constant times n over s to the power constant times s. So still define xj to be, so xj I will be equal to 1 over s if the index I is in Sj, and 0 if I does not belong to Sj. Is there a question? Is something incorrect on the board? Okay.
Do we use larger or smaller? Because on the slide it was small.
Thank you. The intersection should be small. They should almost not intersect. All right. So what we mentioned is that we have the L1 norm of any xi is equal to 1. What is the L1 2 norm, in fact, of any xi? Well, it's 1 over square root of s. The L2 norm squared will be s times 1 over s squared. I said 1 over square root of s. If I look at xi minus xj, so again we said that the L1 norm is larger than 1. What is xi minus xj in L2 norm? In fact, wait. Yeah, I need the L2 norm as well. Okay, so again, the support is of size larger than s. So that should be 1 over square root of s. Tell me if you agree. Support of size larger than s. Each on the entry is 1 over s. So when you square them, 1 over s squared times s, 1 over s, and then take the square root afterwards. All right. So now the claim is the following. So 1, if I consider the xi, so Okay, so this set is the L1 ball intersected with the L2 ball scaled by a factor 1 over square root of s. Right? We know there are things in there, those vectors, for example. Okay, so then I scale it with some rho, and we will see what rho needs to be later on. And I apply A to that. So this from 1 to n, so I've got n subsets here, which stands in R to the power m. The claim is that they are disjoint. So why? Suppose that for some, for some I not equal to j, there is something in the intersection. So let me call it y, and so something which is of the form a of xi plus rho z, but also can be written as a of xj plus rho z prime for some I not equal to j, and for some z prime in this L1 ball intersection L2 ball scaled by square root 1 over square root of s. So suppose that this happens. Okay, so I'm going to look at xi minus xj in L2 norm. On the one hand, I know that this is larger than 1. It's here, 1 over square root of s. On the other hand, I've got xi, xj, so I can introduce rho z prime, etc. So I can write this as, say, y minus xi plus rho z minus delta of y. So delta is the reconstruction map. I would have, so xj plus rho z prime minus delta y. And I would have rho z and rho z prime. So in fact, it's this minus that, right? So that we've got xi minus xj. Those goes away to delta of y. Then we have this thing here, so I need probably to subtract this. But in any case, I'm going to use triangle inequality. So here we have this bound. Now, I have to use my assumption at some point. Well, y is the measurement we make on this vector and also on that vector. Okay, so the reconstruction is stable with a factor c, so that will be c over square root of s. Remember that I took p equal 1/2 sigma s of xi plus rho z in L1 norm plus c sigma s of xj plus rho z prime over square root of s. And then here I have rho times z L2 norm plus z prime L2 norm. So I approximate this by an sparse vector. The best approximation I can get will be better than the approximation by xi. Right? So I will have c rho and then the L1 norm of z over square root of s. Same thing here. And here I have rho times the L2 norm of z times the L2 norm of z prime. Now z and z prime belong to this set. The L1 norm is less than 1. And the L2 norm is less than 1 over square root of s. So if you look at what you have 2c plus 2 times rho over square root of s. Okay, I want a contradiction, but I get the contradiction if I take rho small enough at the beginning. So rho is 4c plus 4. And then that becomes 1 over 2 square root of s. But that cannot be larger than 1 over square root of s. Okay, so contradiction here. So that's one thing about this family of subset of Rn. They are disjoint. Another thing is that they are included in the so I simply write this square bracket for this set here. This is intersection of balls. Now xi itself is in the L1 ball intersection the L2 ball of the square root of s. Okay, so xi plus rho times that. Now, if you look at, say, a vector here, if you look at its L1 norm, it will be less than 1 plus rho. And if you look at the L2 norm, it will be less than 1 over square root of s plus rho over square root of s. So overall, this will be included in this L scaled set, scaled by 1 plus rho, and then you apply A. Okay? So now we will again use some volumetric argument, but we use some volumetric argument in Rm and not in a quotient space. So we're a bit more comfortable doing that, right? Because so what we're saying is that if we look at the volume of the union of those sets that are disjoint, the union from 1 to n. So it's equal to the sum, right, from 1 to n, because they are disjoint. So you take the sum of the volumes. And the volumes of each of them, well, here is the subset. Here is just a translation when you add a of xi, so it doesn't enter the volume. Then you have this factor rho. And when you inflate something by a factor rho in dimension m, the volume is multiplied by rho to the power m. Right, so times the volume of this set here. Okay, do you agree with that? So that's because of the disjointness of those sets. Now, this will be because this union is included in 1 plus rho times a of b1 intersection b2n over square root of s. This volume is smaller than that one, right? One set is included into the other, and this then will be, for the same reason, the scaling factor will come out to the power n, m, and in fact here it was a volume of A applied to that, and here again it's a volume, it's the same volume, A applied to this intersection of two balls. Okay, so simplify by the volume to get so what do we obtain? We obtain that n times rho to the power m is smaller than 1 plus rho to the power m, or in other words, that n is smaller than, so this divided by rho, that will be 1 over rho plus 1 to the power m, and it remains to take the log. Okay, so ln of n will be smaller than m times, or let me write it as log of 1 plus 1 over rho times m. And what did we know about n right from the start? Is that n is large. In fact, is larger than n over 4s to the power s over 2. So the log is larger than s over 2 times log of n over 4s. We are basically done. Rho is a constant. It's I think we chose it as 1 over 4c plus 4, but c was a constant that was given. Is the constant involved in this stability estimate. And what that tells you is that m is larger than some constant times s, and again times this log factor. Okay, so here is a more direct way to prove the optimality of those compressive sensing results. I still showed you the first bit nonetheless, because historically this is through Gelfand width that this was obtained, and then the relation with this concept from geometry of Banach spaces is important, but you don't need to know that anymore if you don't want to. Okay. So any questions on that? The this combinatorial lemma that I really stressed, as you can see, it's really the key. It's really the key. All right. And so I'm going to finish with the following remark, because you might have wondered that all week. So why, when I write those reconstruction bound, I always write the error of best approximation in L1 norm. Well, I play with P on the left-hand side, P between 1 and 2, but this always stays, this index always stays a 1. Is there a reason for that? And the reason, yes, there is a reason, that you won't see anything else than 1, or at least not in the uniform setting, is the following reason. So this, I mean, really what's important would be here in the argument I would give you, but just a bit of terminology. When you consider arbitrary A and delta, if you have a reconstruction estimate of this type with P, so I wrote Q and P here instead of 1, with a proper exponent on S, you say that you have that the pair is instance optimal over the S with that constant C, so in LQ, LP. Okay, so when can that happen? In fact, there's an if and only if condition very close to the null space property. So fix the matrix A, and then when does there exist a reconstruction map making that pair LQ-LP instance optimal of order S? Well, if this happens, then we have this following property. So for all V in the null space, the LQ norm of V has to be smaller than that same constant over the same power of S times sigma 2S of V in LP norm. So the best 2S approximation of V in LP norm. And conversely, there is a partial converse. If this happens, then there exists a reconstruction map, not necessarily a practical one, making that pair A and D LQ, LP instance optimal of order S, but the constant change from S, so from C to 2C. But basically, given A, the existence of a reconstruction map that provides you the stability estimates in the sense of LQ, LP optimality is equivalent to a property just of the null space, right? And recall that given A, the fact that delta 1 provides you a stable recovery is also just a property of the null space of A. All right. So I'm not justifying that, but I'm going to use it for the following claim. If your dream was to obtain instance optimality with a 2 here and a 2 here, so L2 instance optimality of order S, with constant, you want that to be an absolute constant, then what will happen is that the number of measurements you need is proportional to n. Right? Probably n over 2, n over 4. But that's quite irrelevant in compressive sensing. In compressive sensing, you want the number of measurements to be much smaller than n. Right? Otherwise, it doesn't make sense. Otherwise, just take the full number of measurements, m equal n, and solve an n by n system. Right? So this situation is irrelevant to compressive sensing, and so I'm just going to show you why this is true, because you shouldn't believe me right now, so you want to see a proof of that. So let's see. This is much shorter than what I've just done. So suppose that, so A is fixed, and you suppose that there is an L2 instance optimal pair. In particular, this property 1 should be true, and let's take it in the for the smallest possible index S instead of 2S. So suppose that the L2 norm of V is less than C over, well, just C, because I take P and Q equal to 2, times sigma. I'm going to take the best one-term approximation of V, and suppose that that holds for all V in the null space of A. All right. From there, I want to show that M has to be proportional to N at least. So let's rewrite this a little bit. If I write, so for all V in the null space of A, and so for all index I from 1 to N, right, sigma S of V, so it's in L2 norm. When I take the square, I will get, so that's smaller than the norm of V2 squared minus Vi squared. Right, the square here has to be smaller than the square there, but sigma 1 of V is the smallest quantity you can get when you take the L2 norm of V minus a 1 sparse approximation of V, basically. Okay? So it means that Vi squared is smaller than over C squared. I would have C squared minus 1 times the norm of V squared. Okay? So let now P be the orthogonal projection onto the null space of A. Right, so if I'm looking at an orthogonal projection, the trace and the rank are the same for an orthogonal projection. Let's look at the rank first. The rank is the dimension of the image space, which is the null space of A. And generically, the dimension of the null space of A is n minus m, but in general is at least n minus m. So the trace of P will be the sum for I from 1 to n of P of EI inner product EI. Okay, the sum of the diagonal elements. That's the trace of P. Now, right, this belongs to the null space of A, and that earlier said that basically V inner product EI was less than square root of, let's write C prime norm of V, where C prime is square root of C square minus 1 over C square. Okay, so this n should be a capital N. So that will be less than the sum for I from 1 to n of C prime times the norm of P of EI in L2 norm. But we have an orthogonal projection. Right, so the norm of P of EI is less than the norm of EI in L2 norm, which is 1. So we've obtained that n minus m smaller than C primes n times. And so rearranging that, we obtain that m is larger than 1 minus C prime times n, with C prime less than 1. Okay, so m larger than some constant times n. This is what we claim. If you have L2 instance optimality from L2 to L2, it means that the number of measurements is proportional to the ambient dimension. That's irrelevant for us. So we don't want that. We'll always see sigma sx in L1 norm. Now I'm going to finish then with this, what I said before, explanation of this term uniform. You will still see L2 norm appear sometimes, but in a different setting. Right? So this is a statement that say, take A at random, then the following is true for all x in Rn, x minus delta Ax less than blah, 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 and sigma with related to an L1 norm. Now you will see, and that is a statement that I call a uniform statement, that we call a uniform statement. Non-uniform will be slightly different. Fix x from the start, then take A at random with high probability for this x, you have a stability estimate. But it's not a stability estimate that is valid for all x simultaneously. If you want the stability estimate to be valid for all x simultaneously, you will never see, you should never see, otherwise there's a mistake, you should never see something else than the 1 norm here. You would see sometimes something else than the L1 norm here if it is a non-uniform recovery estimate. Okay, and so that concludes the tour of compressive sensing that I've given you. So my personal take on that. What I consider to be really the important foundation. There are many more things. We could give further winter or spring school and summer school to continue that. A lot of other informations to be given. It's a very active field, but I think those are in my mind, the most important and also most accessible things that I could present. So I thank you for your attention. I hope that I captivated your attention for the past week. Thank you.
Yeah, I guess there's not a lot more to learn on this.
Uh-huh.
But presently, I guess there are like 10,000 papers out in this field, so a lot to read.